In the first part of the film, we identified certain objects that regularly appear in polygonal complexes. The very existence of different yet consistently occurring groups of objects implies the presence of recurring principles in their creation, the existence of regular rules. Some of these rules are easily recognized because they are simple and understandable to us. Others are less clear, and explanation for them is not always readily available. Moreover, there is a large group of rules that strictly regulated the creation of polygonal masonry, blocks, and complexes, yet understanding why it was done in a particular way rather than another is sometimes simply impossible. Furthermore, some of these rules contradict the principles we use in construction today. Among the rules followed by the creators of polygonal complexes, the principle of load distribution in masonry is entirely understandable. The load vectors, particularly in masonry composed of freeform blocks, are directed not only downward but also sideways. As a result, the loads are distributed much more evenly than in conventional masonry. The same category of rules includes the method of overlapping niches and openings. As a rule, solid rectangular blocks were used as niche coverings. We use a similar method today. The reasoning behind reinforcement measures, or the skeletal structure of buildings, is also quite clear. Numerous data suggest that polygonal masonry walls did not possess sufficient stability and strength on their own. For example, during earthquakes or foundation subsidence, forces may arise that stretch the masonry in the horizontal plane. If no additional measures were taken to secure the position of the blocks within the masonry, walls built from freeform blocks could easily collapse. Masonry composed of rectangular blocks resists such forces much better. Despite significant horizontal displacement of the blocks, the wall largely retains its shape. To avoid such problems, the rear parts of the blocks were embedded into the embankment. The inclination of the masonry also served as a means of securing them. For example, facing stones leaned against embankments due to their tilt. These embankments could be either artificially constructed or natural rock formations. In buildings, sloped walls address the same issue but in a slightly different way. It is observable that in structures, rows without additional reinforcement have a slight inward tilt, which prevents the blocks from shifting outward. Thus, walls built according to this principle essentially support themselves. Clearly, without such measures, polygonal masonry would not have been as stable or durable. Notably, the destruction of polygonal masonry, especially from freeform blocks, did not necessarily require seismic activity. Ground subsidence caused by erosion, as seen in Sacsayhuaman, was sufficient. Once this occurred, the masonry began to collapse immediately. Other examples illustrate that polygonal masonry itself did not play a decisive role in increasing seismic resistance or structural durability. For instance, the lower part of a tower in Machu Picchu, built within cavities of the rock foundation, is faced with polygonal masonry. Here, it is evident that if anything is supporting, strengthening, or protecting the structure, it is the rock supporting the polygonal masonry, not the other way around. This aspect is closely linked to the rule regarding the use of different types of blocks. Freeform blocks were not used for rectangular buildings, as structural issues could arise during wall construction. Without the support of an embankment, masonry of this type lacks sufficient stability. If a building were constructed in this manner, it would be structurally weak and, consequently, short-lived. For the same reason, facings made of freeform blocks were often reinforced at wall ends and corners with megaliths. Where megaliths were unsuitable, such as around openings, rectangular block masonry was regularly used instead. A different group of less understandable rules includes, for example, the alignment of niche boundaries at a consistent level. If the upper level of niches in a section did not match, builders adjusted the configuration of the coverings. The lower level was also regulated, either by removing part of the material in the blocks forming the lower sections of the niches or by adding individual inserts. The reasoning behind these actions is not always clear, but it is evident that considerable effort was sometimes invested. Rules concerning niches also include their placement across various structures. In buildings, niches almost always face inward. In platform facings, they naturally face outward. On terraces, niches are absent. The third and largest category consists of rules whose meaning is vague or entirely unclear. For example, all structures within a given complex are made from the same type of stone. Additionally, all observed buildings are single-story. This group also includes the method of joining masonry to the ground, either on a rock foundation or on a cushion of stone. Most often, both methods are used within a single complex, making it impossible to link them specifically to seismic resistance. It seems more likely that these methods were chosen based on the function of the structures, ensuring a suitable connection between the masonry and its foundation. Furthermore, the fact that regularly constructed double-row masonry was built without interlocking bonds would be considered a major defect by our standards. It is unclear why such a simple and obvious technique, which would have significantly strengthened the structures, was not used. Especially considering that builders were well aware of interlocking methods, it is frequently observed in openings and niches. However, in the masonry itself, it is almost absent, pointing to some unknown intent. There are also instances of misalignment in single-row masonry, where vertical joints coincide. This raises a reasonable question: how aware were the builders of the risks associated with such decisions? And if they were aware, what guided them? What could have been more important than structural strength? Also worth noting is the unique method of creating walls of varying thickness. Double-row masonry was often constructed with incomplete joining at the rear sides. The gaps between them were filled with fine-grained material. This helped secure the position of the blocks within the masonry and likely compensated for the lack of interlocking rows. This method also allowed for the construction of walls of any thickness. The space between masonry rows could be expanded as needed. In this case, the masonry rows essentially functioned as facings. This group also includes the fact that knobs and bosses are predominantly located on the lower parts of blocks and megaliths. There is an example where this rule proves useful to us. It allows us to identify a clear case of secondary use of blocks and megaliths. For instance, in Ollantaytambo, in the structure known as the 6 stones, the megaliths are turned on their sides, while the small inserts between them follow this rule. On these inserts, the knobs are positioned exactly where they should be, on the lower parts of the inserted blocks. Signs of secondary use can also be observed in other parts of this structure. Another consistent feature related to knobs is that they are almost never found on terrace facings. A rule with a more mysterious implication is the lack of standardization among blocks. In the polygonal complexes of Peru, this principle is never violated. It is evident even to the naked eye that all blocks, including rectangular ones, vary in mass, size, and configuration. This can only mean one thing: each block was individually crafted. And this was done despite the immense volume of masonry and the sheer scale of the structures. Moreover, different types of stone were used. If standardized blocks had been used, construction would have been significantly simplified. But this was not the case. Instead, the exact opposite approach was taken. This suggests that the lack of standardization was not accidental but a crucial requirement. A logically consistent implementation of some fundamental principles behind the construction of polygonal masonry. Another relevant observation is that as the masonry rises in height, the size of the blocks decreases. Regarding the blocks themselves, several systematically observed features are so important that it would not be an exaggeration to say that where they are absent, there is no true polygonal block. The most significant of these features include: the surfaces of the block's side faces are always curvilinear. The rear parts, embedded in embankments, always have the appearance of rough, fractured stone. Parts of the side surfaces that do not participate in the jointing process can also have a rough, fractured appearance. The perimeter of each block consists of a combination of receiving and responding sides. The edge profile of a side forming a joint does not replicate the curvilinear configuration of the side surface itself. This last point is especially important. We will return to it later. It deserves not just a mention but a thorough examination. Among the listed observations, several must be highlighted in particular. The first is elementary and fundamental. It pertains to the masonry itself. The masonry is created not from a single block but from multiple blocks forming joints. The second, the blocks involved in these joints have receiving and responding sides. The third, the general shapes of the side surfaces of interlocking blocks correspond to each other. These three fundamental components form the core principle of polygonal masonry. It can be defined as the rule of receiving and responding profiles. Many aspects of block placement are so rigidly determined by this rule that no alternatives are possible. In some cases, it also has a practical application. For example, it helps to clarify the sequence in which the blocks were installed. And since the perimeters of the blocks are formed by receiving and responding profiles, this rule makes it possible to trace the transformation of a rough stone into a fully integrated block. Thus, the side surfaces of polygonal blocks can be classified by function as receiving and responding profiles. The receiving profile is essentially the seating surface for the next block in the masonry. The responding profile is the side of the next block, whose shape must match the designated seating surface. The seating surface can be entirely located on a single block. However, more often, it is formed by two or even three adjacent, already interlocked blocks. In this case, the seating surface is not a random collection of surfaces from closely positioned blocks but always a unified surface, aligned to a single, common level for all contributing blocks. It often gives the impression that these seating surfaces were created in a single stroke, so seamlessly are the surfaces of different blocks integrated into a unified configuration. The levels of these surfaces match perfectly. Every such receiving side configuration serves as the precursor to a future joint between blocks. Once the corresponding responding block is placed, this configuration transforms into a characteristic interlocking profile, the profile of the joint. The profile of the seating surface, in simpler terms, the receiving profile, forms a specific silhouette when viewed from the facade. By isolating this silhouette, we can describe the overall shape of the receiving profile and gain insight into its structure, even without disassembling the masonry. This is because the essential features of the profile remain consistent throughout the depth of the joint. This raises an important question. Why is the receiving profile always oriented in such a way that it presents its key surface configuration details to the observer? One possible answer is that the observer, standing in front of the masonry facade, is positioned exactly as the creator, or whatever mechanism, was when the masonry was built. Since no alternative configurations, such as a receiving profile positioned above within the masonry, are known, it can be assumed that the facing the facade position was, for some reason, the only feasible option. The configurations of receiving profiles are diverse, ranging from completely straight to S-shaped. Among them, several well-defined types with specific variations consistently recur. Straight receiving profiles, for example, appear either as an absolutely straight line or as a line with a slight curvature. Horizontal, vertical, and even diagonally aligned straight joint lines are formed precisely by this type. Receiving profiles with more pronounced curvature form a different type with its own characteristic features. It can be conventionally called the arc type. Next, we can distinguish a profile resembling the Latin letter L. The bend angle of this profile can be right, obtuse, or acute, with varying degrees of rounding, either smooth or sharply defined. The angle can also be truncated with a straight line. A variation of the L profile is a receiving profile shaped like an inverted step. The next receiving profile configuration resembles the Latin letter U, except that one of its vertical segments is shortened. In some cases, the shortened vertical is so small that it appears more like a modified L profile. Such a seating surface usually fills a deep recess and grips the side of the block adjacent to it from above. The final type of receiving profile has a shape close to the Latin letter S. Conventionally, it is referred to as the S profile. Identifying receiving profiles as distinct objects allows for solving several questions. The first, as previously mentioned, is determining the order in which blocks were laid. For example, in this section of Saxahuaman, the second row could only have been laid in a numbered sequence, and only progressively, as the corresponding receiving profiles were created. The second concerns claims that the material of the blocks was malleable, like clay, during installation, which supposedly enabled the formation of phenomenally tight joints. However, the rule of receiving and responding profiles clearly demonstrates that the precise fit of polygonal block joints is the result of deliberate preparation of the side surfaces of solid stone blanks. The third point is that the creators of polygonal masonry clearly adhered to natural principles of minimizing labor effort. These principles are well observed in biological structures, for example, in the cellular tissue structure or the vein arrangement in a dragonfly's wing. That this principle was applied can be demonstrated by calculating the length of joints in cases of right angles versus curved edges. The result shows either equality or even an advantage in favor of curved profiles. In addition to the mentioned types of receiving profiles, there are also examples of extremely complex joint configurations. When analyzing these profiles, it appears that there was no single template for their design. Each profile seems to have been created based on the specific situation. There were no strict limitations apart from those dictated by the shape of the stone blanks or the configuration of the masonry itself. This could very well have been the case, given that all the blocks were different. As a result, the entire logistics of placement naturally followed from this condition. Moreover, it seems that the selection of stone blanks was not particularly meticulous. Most likely, the material that arrived first at the construction site was used. However, working in this manner would require a well-coordinated logistical system and the appropriate tools. The tool aspect is especially intriguing. It would have needed to shape stone into any configuration and penetrate to any depth. It is also worth noting separately that the presence of blocks with complex side configurations directly contradicts the concept of impact-based technology. If blocks were produced using mechanical processing, such as hammering with stones, the most rational approach would have been to shape them as close to parallelepipeds as possible. However, in reality, we see something entirely different. The next group of objects with its own set of regular rules is boss-like protrusions. Depressions are often found on the lower parts of blocks. The purpose of these depressions and how they were created remains to be studied. On blocks, they most commonly appear in pairs, while single ones are much rarer. Above these depressions, excess material often forms protrusions of varying prominence. Analysis of their placement and the many stages of their evolution preserved in stone suggests that they served as preforms for bosses. One particularly characteristic feature is frequently preserved unchanged, standing out clearly on the underside of finished bosses. A concavity left from the original depression. For example, here, most of the depression has been removed, the side and lower sections, but traces of it remain in the form of a slight indentation and a remnant of the partition between the depressions. And here, vertical traces of material removal at the partition between the depressions are clearly visible. Some bosses were created from the material of the partition between two depressions. Such bosses are positioned either at the center or closer to the center of the lower portion of the blocks. This is a good example where a boss was formed from the partition material between depressions. Not only are traces of the former depressions still visible, but part of the partition itself remains. In the first image, the angle allows for various interpretations. But when viewed at a half-turn, the possible explanations narrow considerably. When a boss is formed from the material above a depression, it is naturally positioned slightly higher up from the lower edge of the block. However, when a boss is created from the material of the partition between depressions or from its side, it can be located very close to the block's lower edge, sometimes overhanging the edge or even sitting directly on the beveled margin surface. Additionally, there are cases where bosses appear to extend downward or sideways. Another method of creating bosses was by shaping them from a long ridge of material above the beveled edge in the lower section of the block. Once the position and shape of the future boss were determined, excess material was removed, both around the boss and across the entire facade surface to achieve the necessary level. In some cases, different stages of material removal can be observed simultaneously in the area surrounding a future boss. For example, in the section immediately adjacent to a developing boss. Similarly, we can see that when the boss forming process has only just begun, the top of the future boss aligns with the level of the block's original surface. These observed patterns allow us to conclude that in all these cases, we are witnessing the process of creating the boss element. not the removal of some residual lump that supposedly connected the block to the quarry bed, nor evidence of quarry work, as some researchers suggest. No, what we see is the intentional creation of a new feature within the block itself. This suggests that such work was carried out only after the block was already positioned in the masonry. There are a few more recurring observations that support this conclusion. First, no blocks with rough, fractured facade surfaces are found to have bosses. Bosses appear only on blocks whose facades have been worked to some extent. Moreover, the more refined the block's surface treatment, the more precisely shaped the bosses appear. Second, the material structure of the bosses visually does not differ from the rest of the block. Furthermore, in many cases, the stone's natural patterns, inclusions, and stratifications, as well as defects, continue seamlessly from the block's surface onto the boss itself. There are no known examples where a transition from the block's body to the boss shows any change in material structure. Finally, it is important to acknowledge a certain difficulty in determining the degree of intentionality behind the appearance of bosses. It is also impossible to entirely rule out the possibility that their formation was a byproduct of some other process related to the shaping of block facades. The next group of regular objects that follows specific rules is prepared block edges. The profile lines are often perfectly straight, without deviations or irregularities. The precision of these profile sections is so meticulous that it creates the impression they were made with a single continuous motion. This is particularly striking given that their lengths can measure in meters. Similarly, many angles within the profiles are also executed without deviations or inaccuracies. This again suggests either a light stroke of the hand, or an extremely meticulous and therefore highly labor-intensive execution of such details. At the same time, when looking at the joining areas, we see that the side surfaces of the blocks always have a curvilinear configuration. They can resemble propellers or even lenses. The degree of curvature varies widely, from subtle to highly pronounced. Thus, we encounter a contradiction. The edges of the side surfaces that emerge on the visible face of the blocks do not continue the shape of the side surfaces themselves. Each has its own distinct and sometimes vastly different form. It is logical to assume that if different parts of an object exhibit strongly independent characteristics, this may be due to differences in their intended functions. In this case, some of these functions can indeed be identified and traced. For example, the interlocking side surfaces of blocks exhibit curvilinear profiles that generally correspond to each other. When these surfaces are fully matched across their entire area, they function as a mechanism to limit the movement of blocks within the masonry. This is the primary purpose of such side surfaces. This type of joint is essentially an analog of a locking connection and helps bind the elements together within the masonry. When reinforced with additional stabilizing measures, as previously discussed, it provides the necessary structural stability for the entire construction. Thus, the masonry we are dealing with is not just polygonal masonry. It is masonry based on curvilinear interlocking joints. Recognizing this principle as a fundamental rule allows us to understand many aspects that previously lacked explanation. For example, the uniqueness of each individual block. In modern construction, we generally use a simpler method. We pre-manufacture standardized elements en masse and then assemble them using binding materials such as mortar. It seems that similar methods could have been applied in polygonal masonry as well. However, such methods were consciously avoided, which means a different goal was being pursued. Yes, the interlocking of curvilinear surfaces cannot fully replace the function of binding materials. To ensure the stability of such masonry, additional measures were required. These measures clearly demanded extra effort and resources. Moreover, they introduced a certain heaviness, complexity, and cost to the construction process, yet the builders accepted this challenge. But perhaps the goal justified the means, and what we see as excessive complexity was actually a necessary and deliberate choice. After all, in addition to stability and strength, there may have been other advantages that are less obvious to us today. It is also possible that there were benefits we are unable to recognize at all. However, some aspects of these less obvious advantages can already be discerned. For example, a structure built using this type of masonry may have been superior in quality compared to one carved entirely from bedrock. This is because avoiding natural fractures in rock formations is virtually impossible. Such fractures would introduce structural weaknesses that are unpredictable in their behavior. Therefore, creating an artificial equivalent with predictable properties was likely a simpler and more reliable solution. By constructing with separate blocks, builders could ensure each element had well understood and controlled characteristics. Polygonal masonry and polygonal blocks fully meet this requirement. Furthermore, it is obviously impractical to carve an entire structure from a single rock formation in its full, necessary configuration. In many cases, sufficient natural resources simply did not exist in the required form or quantity. In some areas, there were no suitable rock formations at all. This suggests that polygonal masonry with curvilinear interlocking joints was a necessary adaptation, a technique developed to compensate for the limitations in the availability, shape, scale, and structural integrity of natural rock formations. It was also a method used to enhance and reinforce their beneficial properties. In other words, this was a technology aimed at modifying and improving the properties of natural rock formations, to the point of creating artificially enhanced equivalents. At the same time, certain objects found across different complexes appear to have been fundamentally irreplaceable by structures made from individual blocks. For example, Intihuatana stones are always represented as solid rock formations. Other examples include structures with a solid rock core surrounded by masonry. As for the edges of the side surfaces that extend to the visible face, their function can also be identified with relative clarity. The edge of a side surface facing the facade is easy to recognize, even if the block is removed from the masonry. It features a distinct ridge. This element may have played an important role in the interlocking of blocks. The issue is that precisely aligning surfaces with varying relief is not an easy task. Furthermore, proper alignment was required both horizontally and vertically. Since this joining process occurred without direct visual control, there was a high probability that surfaces would meet at an imperfect contact point rather than achieving full alignment. However, full interlocking of the corresponding reliefs was essential. If this was not achieved, gaps would remain between the joined surfaces where their configurations did not match perfectly. To ensure an absolutely precise, tight fit, a marker system was required. By using the edges of the joining surfaces as alignment markers, the process was greatly simplified. To achieve a fully interlocking joint, builders only needed to align the designated edges of the blocks. Thus, each of these elements, the side surfaces and their prominent edges, had specific functions. And it is clear that these functions had to be strictly followed, otherwise, the quality of the joints and the masonry as a whole could not have been guaranteed. But since these are different, independent components of a single object, each with its own functional role, does this mean they could have been created separately? Were the side surfaces shaped independently of the edges that extended onto the facade? And if so, in what order was this process carried out? If we assume that the side surfaces were shaped first, with all their curvilinear details, then their edges would naturally follow the created relief. In this case, it would be impossible to make them perfectly straight without affecting the side surface itself, because we are dealing with a solid material. As a result, only edge profiles that naturally formed from this process would be possible. But since what we actually observe in reality is different, this option does not seem to apply. A completely different result would be achieved if the straight edge was created first, and only afterward, using it as a reference and without altering its configuration, the rest of the side surface was processed. However, in this case, one very important condition must be met. We recall the rule. The side surfaces of interlocking blocks correspond to each other in their main curvilinear configurations. To implement this rule, where one block has a lowered surface level, the corresponding block must have a raised surface level. Since we are working with solid material, we must have the ability to both lower and raise the surface level. This requirement can only be met by ensuring an excess volume of material. This means that the blocks must have been delivered to the construction site in an unprocessed or nearly unprocessed state. Evidence that the original state of the blanks allowed for such an approach can be seen directly in the rear sides of many blocks already in the masonry. When the rear parts of blocks are embedded in the rubble core, they always have the appearance of rough, fractured stone. By this feature, it is easy to determine the past position of a block in the masonry, even if it is no longer in place. The same pattern can be observed in double-row masonry. Here, the front-facing parts of the blocks have been processed, while their rear sides have clearly not been touched. Many similar examples can be found in Saxe-Heumann. Many blocks installed in the zigzag masonry have exposed rear sides. For most of these blocks, the rear surfaces also appear as rough, fractured stone. Blocks showing signs of rear surface processing do exist in the zigzags, but they are rare and do not change the overall picture. Rather, they indicate that such blocks may have been specially prepared for some additional function. From these examples, we can see that unprocessed rear sides, as well as unprocessed parts of the side surfaces that do not participate in interlocking, are a regular phenomenon. Furthermore, signs of unprocessed areas can also be found on the front-facing surfaces of blocks. In the zigzags of Saxe-Heumann, many blocks have front-facing surfaces that are far from perfect. In many cases, the front-facing surfaces only have the most basic configuration. Sometimes they are not processed at all and appear almost identical to the rear surfaces. On such blocks, only the edges appear to have been processed. Thus, we have clear evidence that the builders used block blanks with excess material volume. Consequently, any assumptions that blocks left the quarries in a perfectly finished state come into question. How, in practice, could they have ensured that, when creating straight, precise profile lines, a certain volume of excess material remained on the forming side surface? There are several simple and fundamentally similar methods. One approach would be to remove material at an angle to the future side surface. Another would be to carve a groove of the required width and depth in the designated area of the blank. In both cases, the section of the block intended for the side surface will automatically retain enough material to create a curvilinear relief. Once the necessary slope is made on a peripheral section of the blank, or a recess for the profile is carved, the rough, irregular surface is replaced with a relief of a defined configuration. By creating this surface without distortions or abrupt transitions, it provides a foundation for straight, even profile sections or for sections with the required curvature, which is important for understanding how the front surface of the block was formed. When creating the profile, the groove was divided along its length. The part of the groove remaining on the block automatically became the edge of the block, and already at this stage, it had a specific cross-sectional shape. The prepared edge, therefore, is the residual part of the slope or recess, groove, the section that remained on the front side of the block after the profile was created. Each method produced a characteristic cross-section of the edge. Grooves left a trace of uniform depth in the form of an elongated depression with an L-shaped cross-section. Slopes, on the other hand, resulted in a smooth or slightly curved cross-section. These methods were used selectively. Grooves were mainly applied to the lower sections of the blanks, whereas slopes were mostly used for the upper sections of the blocks. Remnants of grooves are much rarer in these areas. Slopes were also commonly used to prepare the surface for profile sections with internal angles. It is possible that the asymmetry of the edges relative to the joint, seam of already installed blocks, which is regularly observed, is related to the use of these different methods. One might assume that the use of different methods was either situational or specialized. However, traces of combined techniques also exist, for example, where a slope was applied on top of a groove. Another important observation is that a groove of a certain width and depth allows for localized focus on a limited area of the future profile. This is a localized recess, and the main volume of the blank on either side of the groove remains untouched. Such examples can be found, although they are not very common, as they were likely an intermediate stage in block creation. They were preserved only in cases where the external appearance of the block was left unfinished. However, in Sacsayhuaman, such cases are not rare, which may indicate that construction there was never completed. It is possible that in some cases, excess material on the front face of the blank was intentionally left. Later, it could have been used, for example, for carving bosses. The presence of an edge is directly related to the presence of an interlocking profile. There are enough examples where slopes were made only in areas where an interlocking profile exists, rather than around the entire perimeter of a block. In such cases, all the sides of blocks that do not participate in interlocking, such as the exposed sides of blocks in the upper row, as well as the lateral surfaces of the blocks, retain their original rough appearance, similar to fractured stone. Their exposed lateral surfaces show no signs of processing. The perimeters of these sections remain unrefined. Accordingly, no slopes or grooves are present, as there was no need to prepare them. And, as a result, no prepared edges are found in these areas. From this, we can conclude that slopes and grooves were made immediately before the creation of each profile, separately in each case and always tailored to a specific profile. This is because the configuration of the edge always matches the configuration of the interlocking profile. It replicates its details regardless of complexity, sometimes perfectly, sometimes with slight variations. Logistics and the sequence of masonry placement also indicate that the prepared surfaces for profile creation could not have been made all at once around the entire perimeter of a blank. Such an approach would have been pointless, as the location and configuration of each subsequent profile only became clear during the construction process. It was a sequential process, where each new step was dictated by the necessity arising from the cumulative result of previous steps. Thus, the final shape of a block's facade was not the result of a single, pre-planned operation but rather emerged gradually through the step-by-step creation of interlocking profiles. Some confirmations of this can be found in the specific characteristics of edge configurations. For instance, otherwise, it would be difficult to rationally explain why the elevations of edges vary despite being linked to their respective profiles. Likewise, the angles of slopes differ, and their shapes vary even on the same block. Additionally, on protruding block corners, at points where edges meet, ridges can often be observed. These ridges, in turn, can be interpreted as the result of separate surface processing with differing inclination angles and configurations. It appears that during the final finishing of the front face, such inconsistencies were smoothed out, so that the edge would form a continuous, uniform feature around the perimeter of the block. This resulted in a clean and aesthetically refined appearance. It seems clear that the final front surface was meant to be slightly convex or somewhat flattened, gently transitioning into rounded edges. Once the profile was completed based on the slope or groove, work could proceed on shaping the side surface with its curvilinear configuration. And the masonry could continue.